Hello everyone, this is chapter 11.9 where we'll be discussing representations of functions as power series. And the first thing I want to recall is the one of the first examples we saw actually for power series, just this geometric series with ratio x. So namely the sum over n equals 0 to infinity of x to the n. So x to the 0 is 1, x to the 1 is x, plus x squared plus x cubed and so on. And remember that this is legitimately a geometric series where the ratio is x. Now, in a geometric series, you can actually find the sum of the series as the first term in the series divided by 1 minus the ratio. We've seen that before. The only problem is this is only valid when the ratio has absolute value less than 1. So only when the absolute value of x is less than 1. So in fact, the interval of convergence for this series is negative 1 to 1, non-inclusive, because notice when it's 1, you just have a sum of 1s. When it's negative 1 to the n, what you actually have is a divergent sequence that we're summing over. So by test for divergence, that diverges. So now what we're going to do is we're going to manipulate things that look something like this end result here and see if we can manipulate it in the sense that we can write it as a power series. And in doing so, the interval of convergence part will actually be pretty easy. And I know that's something we kind of focused on in 11.8 a lot, but here with this in mind, it's actually not too bad. So first let's look at this one. This is 1 over 1 plus x squared. And what we want is 1 over 1 minus something. So notice right away we can write this as 1 over 1 minus negative x squared. So this is our x. So we're replacing x, everywhere we see an x in this expression above, with negative x squared. So namely, we can write this as the sum from n equals 0 to infinity of negative x squared to the nth power. And this is only valid when the absolute value of negative x squared is less than 1. And in fact, this is actually a pretty simple thing to look at. So notice, the negative part can be removed because the absolute value of negative x squared is the same as the absolute value of x squared. And the absolute value of x squared is the same as the absolute value of x then squared. All right? And even though the absolute value of x squared is always positive, x itself could technically be negative because after squaring it, its absolute value can still be less than 1. So this still gives us this. Meaning the interval of convergence technically is just negative 1 to 1. And how I know it's exclusive to negative 1 and 1, well, you can plug them in and see what happens. Negative 1 squared is positive 1, which is, well, then the negative hits, so you get negative 1 to the n. In fact, you'll kind of see that no matter what you plug in, you'll get negative 1 to the n, for the endpoints anyways, which diverges by test for divergence, as we saw previously. So this really is the answer, but there's actually a nice way of writing this out. What you can do, we've kind of seen this idea before. You can split up the inside as negative 1 times x squared. Since they're both taken to the nth power, this is negative 1 to the nth times x to the, x squared to the n, which is x to the 2n. So if you actually wanted to write this out, you can write it as, starting in 0, you get, let's see, it's positive x to the 0, so it's 1, minus x to the 2 plus x to the 4th, minus x to the 6th, and so on. It alternates because the negative 1 to the n, and the powers are purely even because the power is 2n. So this is actually really nice to see. I prefer writing it like this because it's more compact, but you may like this way of writing it as well because it's more intuitive, I guess. And then I'm not going to box the interval of convergence, but it's nice to keep that in mind. Okay, now moving on to part 2 here. We want to do the same idea, but the x cubed on the top kind of confuses things because we want 1 on top. So that's actually not too big of a deal. We'll just move x cubed off to the side so that we have 1 on top. So that's actually fine. But notice in the bottom, if we rearrange them so that we have the constant first and then x, that's okay because we have 2 plus x. And we can make it a minus, but again, 2 confuses the issue here because we want there to be a 1 there because we're mimicking this. 1 over 1 minus x. 1 over, this is 2 plus x. The plus is fine because we can write it as a double negative. That's okay. But the 2 gets in the way. So what we can do now is we can actually pull 2 out. So if you pull 2 out, you're dividing these by 2. So notice x divided by 2 is x over 2. 2 divided by 2 is 1. And I'm going to rearrange them like this. So this actually isn't too bad to motivate that we would want to do something like this. And the 2 in the bottom we can pull out below this x cubed, and we end up with this. And of course we know from the previous example that this is the same as 1 minus negative x over 2 in the denominator. Great. So with that being said, we can actually write this as a power series. The x cubed over 2 is on the outside, but then on the inside, we're summing over, well, n equals 0 to infinity, of this, because this is our x from the general expression here, to the nth power. So it's negative x over 2 to the nth. I hope that made it on the board. Yeah, you can see that, good. So now I'm going to split this up a bit, and I'm going to bring these in after the fact. But let's kind of see what we can do here. Let me board this off. So we get x cubed over 2, sum from n equals 0 to infinity of, so if you break this up, remember the top is negative x, but that's negative 1 times x. That's negative 1 to the nth, x to the nth, over 2 to the nth. So if you split it up amongst the powers, you get that basically. Now bringing x cubed on the inside is just distribution, same thing with the over 2. And what that really does, it accompanies the powers of the same base and adds to the exponent. So we end up getting here is the sum from n equals 0 to infinity of negative 1 to the nth, x to the n plus 3 over 2n plus 1. Cool. And this is, well, our answer. This is the power series representation for this function, which is kind of cool to actually see that. Now, as far as the interval of convergence goes, all I'm going to say is the following. This converges when the absolute value of the original base, negative x over 2, is less than 1. Now again, since it's absolute value, we really don't need the negative, so you can ignore that. And we know this is the same as absolute value of the top over absolute value of the bottom. Absolute value of 2 is just 2. And then multiplying that to the other side gives us this. We actually have a radius of convergence of 2. So I'm not actually going to write out the interval of convergence. You can do that on your own if you'd like. But we have a hunch it would be negative 2 to 2. But it's nice that we see something that looks a little different compared to what we've kind of seen so far. This looks very similar to what we saw here. This looks way different. So that's kind of nice. And in fact, if you plug in certain values for x, you'll actually get specific sums, which is pretty cool. The only thing is that, honestly, this is just a geometric series. So, for instance, if you plug in x equals 2, or x equals 3, or whatever you like, well, it has to be less than 2, though, doesn't it? So let's say you plug in x equals 1.5, or 3/2. If you do that and try to simplify the inside that we're summing over, the general term we're summing over, really what we'll get is really just a geometric series. And really, so far, these power series representations of functions are just geometric series. Now, why I bring that up is because what we're going to do now is we're going to try to modify our technique here a little bit, in the sense that I'm going to give you a greater tool we can use. Yes, we're going to get calculus in the mix now. So now what we can do is we can take a function, take its derivative or antiderivative depending, to try to mimic this form and then write it as a power series. Crazy. So with that being said, we'll get actually exact forms basically for a series that aren't just geometric. So let's take a look at that right now and see if we can look at some specific examples to see if we can get a handle on what I'm talking about. Right, so this is what I was just referring to just now. So this theorem says that if we have a power series with a radius of convergence r, then the following are true. The derivative with respect to x of the power series is the sum over the derivatives of each general term, or each term in the series. And the integral of the power series is the sum over the integral of each term. Which makes sense because if you have a series, it's just a sum of terms. And if you want to take derivative of the sum, you can just take the derivative of each one. Same thing goes for antiderivative. Now, in reality, to actually pull that off, you essentially need, well, not necessarily absolute convergence, but you need it to be convergent. But power series, as it turns out, are really good examples of series in the sense that they abide those rules, or we can take the derivative of each term and we can integrate each term, actually, as it turns out. Now, something to keep in mind here that I didn't write, I probably should have, is that both of these have the same radius r. So let me say same radius of convergence as the original power series, which is r. The only issue is that they may still be convergent at x equals r, well, for the endpoints, really. So we still need to check the endpoints here. Which I think is important to note, because if you look at the previous examples we saw, I kind of gave you the idea that you don't need to check the endpoints because it'll always be open. And that's actually true. That's actually the case. But here, when you take derivative and antiderive, though we still have the same radius convergence, the endpoint may not necessarily be divergent or convergent there. So when you take derivatives or antiderivatives, you do need to check the endpoints. Otherwise, you don't really actually. But anyways, enough with that. Now let's actually see an example of this. Actually, there's a little more I can say, because we can actually take derivatives. So I'm just going to show real quick. So with this top one, this is the sum over, let's see, derivative of a constant times this is just the constant c sub n. And then derivative of x minus a to the nth is n x minus a to the n minus 1. By chain rule, derivative of x minus a is just 1, so nothing really happens. But notice, if you start from 0 to infinity and plug in 0, this n that's multiplied makes the whole term 0 when n is 0. So in fact, when you take derivative, you actually start at 1 instead of infinity. If you started at 0, you would just have a 0 term by default. So it's okay if you don't write n equals 1, you write n equals 0. But it's just having that in mind, that when you take the derivative, you lose the first term because it's a constant, basically. All right. So now with antiderivative, very, very similar idea. So this is from n equals 0 to infinity of, well, same thing. Cn x to the a, or x minus a, to the n plus 1 now, and then divided by n plus 1. Now, a few things are kind of funny here. So notice I'm just using the power rule, well, the antiderivative version of the power rule anyways. Add 1 to the power, divide by that. And again, because the inside's x minus a, whose derivative is 1, by chain rule there's nothing you have to divide by, or there's no real point of doing a u substitution because the derivative of x minus a is still just 1. But there is something kind of funny that happens. When n is equal to 0, you actually basically just get, kind of think about what's going on. When n is 0, this is just c sub 0. When n is 0 here, you get c sub 0, that to the 1 over 1. But you know what we're actually kind of missing is when you take antiderivative, you always need a plus c if it's a general antiderivative. So if it's a definite integral, basically. So in other words, since there are no limits, with antideriving, we need the plus c. It's kind of what I was trying to say. So really, when you plug in n equals 0, that doesn't affect this part of it. This is just a consequence of definite integrals. All right, so now with all those details out of the way, now let's focus on this example here. So I want to express this function as a power series. And to do that, what I'm going to notice is something that's not super obvious at first hand, but remember that we have this. We have this power series 1 over 1 minus x is equal to this. Good. Now, also notice that if you take the derivative of both sides, coincidentally, derivative of this left-hand side is actually equal to this. So just to show that, let me denote that by taking derivative of both sides. Actually, you know what? Let me do this. Let me just use an arrow in d over dx. So we're going to take derivative of both sides of the equation. Now, this is really 1 minus x to the negative 1, and its derivative with respect to x is then what? Well, by power rule, it's negative 1 to the, of 1 minus x to the negative 2, because you bring the power down and subtract 1 from the power. But then by chain rule, derivative of the inside is negative 1, and then it cancels this, and what we're left with basically is just 1 over 1 minus x squared. So derivative of the left is 1 over 1 minus x squared, which is exactly what we want to find the power series representation of, so that's good. Here, taking derivative of this is the sum from n equals 1 to infinity now, because we lose a term when we antiderive, when we derive, opposed to when we antidifferentiate, we gain a term. So that's kind of the reason why here it starts at 1 instead of 0, and here why it still starts at 0, but there's a new term c now. And derivative of x to the n, of course, is n x to the n minus 1. So this is the power series representation. And if you want to find the interval of convergence, well, it'll still be the same as this interval of convergence, well, this radius of convergence anyways. So it's still r equals 1 for the radius of convergence. So let me write r equals 1. Now, as far as the interval of convergence, though, we actually have to check by plugging it in and seeing if the endpoints work. And in this case, you can kind of tell plugging in ones, well, you just get the sum over n. And if you plug in -1, you get an alternating sum of n's. So those both actually diverge. So the interval of convergence here is still -1 to 1, not including either of the endpoints. Okay, now I didn't write out the terms. If you want to write out the terms in each of these, you can do that. And it's nice to see, because if you take the terms of these, you'll get 1x, x squared, x cubed, and so on. And if you take the derivatives, you'll just get these ones, which are, well, if you plug it in, you'll actually see what it is. But it's, let's see, it's going to be 1, 2x, 3x squared, and so on. So those are just, of course, the derivatives of x, x squared, and 3x, and again, beyond. So now we're going to take a look at more examples, so let's see how crazy this can get. Right, so now these are very specific, very useful examples. These are kind of classic scenario cases. The function ln of 1 plus x and the function tangent inverse of x have very, very nice power series representations, and you can actually find them by the techniques we just saw. So the first thing I'm going to notice for the first part here is I'm going to take its derivative. So when I take its derivative, how do you undo the derivative to get back to this? Well, notice this is equal to, basically, the integral of the derivative. So the integral of the derivative of ln of 1 plus x. There are a little bit of issues I have with this, just because, well, in order to pull this off, we have to make sure that the constant is 0 and so on. Because when you antiderive, you get a new constant, and you have to make sure it lands back where it is. Now, the derivative of ln of x is 1 over the inside, so that's going to be nice. But what I'm going to do, instead of like viewing it like this, I'm just going to say take its derivative, and then we'll get f prime, and then antiderive to get back to f. So let's do it that way instead. So let's see if we can follow. So I'm going to take its derivative, both sides of the equation. So on the left, we just get f prime of x. On the right, we get 1 over 1 plus x. And the reason why we're doing this is because we're trying to aim for a power series representation. And this is a good one, because notice this is 1 over 1 minus -x, which we've kind of seen actually. And in fact, this has the power series representation -x to the n from n equals 0 to infinity. And notice this is just the same as the sum from n equals 0 to infinity of -1 to the n, x to the n, if you split it up. So that's fantastic. But that's f prime, that's not f. But notice, if we antiderive this, we get f. So the let's say that f of x is equal to the antiderivative of f prime. We have a few things to kind of sort out here just because of the constant scenario. But this is definitely true. And since we know f prime is this power series representation, then now basically what we can do is pass the integral through the sum and take the integral of the general term here. So what we get is the sum from n equals 0 to infinity of the integral, I should say dx here, by the way. There we go, that sounds better. And we have -1 to the n x to the n dx So now to take the antiderivative of each term, we're going to use the power rule, add 1 to the power of x, and then divide by the new power. Negative 1 to the n is just a constant with respect to x. So the negative 1 to the n part we don't really care about as far as antiderivative. That just kind of comes along for free. So we end up getting this, negative 1 to the n, x to the n plus 1 over n plus 1 is basically what we get here. Now again, when you antiderive, there is a plus c technically. So you get a new additional term. Now, as it turns out, c in this case is 0. And it's not hard to justify that. So here's what I'm going to do. I'm going to clean this up just because I want to keep space for the bottom part. So we may need to do something similar once we get there. But I'm going to clean this up and I'm going to bring this here because we have equality now. But then there's a little more we can do beyond this. Right, so I have it cleaned up, and the first thing I want to say is I want to justify the c as 0 by plugging in x equals 0. So notice when we plug in x equals 0 on the left, we get ln of 1, which we know is 0. On the right, we get the sum over just zeros, and then plus c. Because when x is 0, the whole general terms are each 0, so for sure we just get zeros there. Even when n is equal to 0, because we'll have x to the 1, and x to the 1 is x, and when you evaluate that as 0, you get 0, as it turns out. So in other words, we get c is equal to 0, so we actually don't need it. So I'm just going to modify that a little bit. And the next thing I want to say is that the radius of convergence is 1, because the radius of convergence of the derivative of this was just the usual power series, which has a radius convergence of 1. So that's not too bad. So in other words, the interval of convergence then is negative 1 to 1. But like I said, we have to check the endpoints. Now, when you check the endpoints, plugging in negative 1 will basically make this negative 1 to the n times negative 1 to the n plus 1. Now, negative 1 to the n times negative 1 to the n plus 1, kind of mentioned this in the previous video, but the negative 1's kind of cancel. Basically, you can write this as negative 1 to the n times negative 1 to the 1. And this is going to be negative 1 to the n plus n, which is negative 1 to the 2n. And notice negative 1 to the 2n is the same as negative 1 to the 2 to the n, which is just 1 to the n, which is just 1. So this all amounts to just 1 here. So basically, when you have two negative 1 to powers, they cancel out and you just get positive. But in this case, they cancel out in such a way that you get negative 1 because the powers were offset. They weren't the same power. Okay, so plugging in negative 1 gives you a negative on top. If you pull the negative out, basically this is just a harmonic series. And the kind of funny thing about this is, well, there's some re-indexing you can do. And in fact, I'm going to erase this just to show that real quick. All right, good. So if you plug in n equals 0, you get negative 1 to the n, which is 1. X to the 1, because 0 plus 1 is 1. So it's just x for the first term, over 0 plus 1 is 1. So really we have this for the first term, minus this for the second term, plus this for the third term, and so on. So the first term is kind of where it takes off. So once you figure out the first term, the fact that these are both n plus 1, really you just get 1, 2, 3 for each of the terms. So it's not too difficult to figure out what happens from there, because if you just add 1 to the previous term, you get that. Good. But now the issue, I think, is that notice this is really the sum from n equals 1 to infinity of x to the n over n with an alternation of signs. And the power should be, it should be n plus 1. And the reason there is because when you plug in 1, you get negative 1 to the 2, which is positive for the first one. And in fact, there's a really nice way of seeing that without actually writing the terms out. Here I wrote the terms out to show it, but something you can do is you can take a look at our original series, and you can decrease all of the n's by 1 and increase your indexing counting by 1. So it's like a balancing of basically recounting. So if you add 1 to the 0 to make it 1, then you have to subtract each of these n's by 1. So I'm replacing every n by n minus 1. So we get n minus 1 there. X to the n minus 1 plus 1 is just x to the n. And then n minus 1 plus 1 in the denominator is just n. And clearly we just get this. Now it's a little different from the way I wrote it here, but notice it still has the same alternating sign part. So in fact, negative 1 to the n minus 1, negative 1 to the n plus 1 are really the same as far as the series is concerned. In fact, they correspond to the same sign changes. Okay, good. So now, here, like I was saying over here for the interval of convergence, when you plug in negative 1, you basically get a harmonic series because there's no alternating part. So this definitely diverges. When you plug in 1, though, well, that x to the n becomes 1 to the n, so that's just 1. Forget about that. And then you get negative 1 to the n minus 1 over n, which is an alternating harmonic series, which actually converges. So that's why I wrote this, by alternating series test. Now, the really nice part about all of this is that since this power series representation of ln of x plus 1 is valid for x equals 1, we get a closed form for the alternating harmonic series. And in fact, I'm just going to show you really quick what that is. So now I say when x is equal to 1, so we're kind of done as far as the power series representation goes. It's this, but I'm going to reindex it because it looks better. So let me write this as n plus 1, x to the n over x to the n, or x to the n over n. And yeah, so that part's fine. But now we can plug in x equals 1. So this is a nice consequence, I should say. So we're done with the problem already. But a beautiful consequence of this is when you plug in x equals 1 into this, you get ln of 2 equals the alternating harmonic series. How lovely is that? So I saved this result until now. So I actually had in a previous video the alternating harmonic series. I said it was convergent. I said we don't know what it converges to yet. I could have told you it was ln of 2, but I wanted to save it for this because the techniques of showing that I think are just so beautiful and wrapped up in calculus mixed with these power series techniques that we're discovering here. And I just think it's a really nice result. Now, tangent inverse actually has a very similar result that's also beautiful in its own right. So I'm going to apply this in the same exact way. So just like what we said for ln, this is, well, the integral of f prime of x. And as a result, we'll get a plus c, but we'll actually find out that c, as it turns out in this case, I believe is also 0, but let's take a look at that. Now, the derivative of tangent inverse is 1 over 1 plus x squared. Good. And we actually know the power series representation of this. We just did that in a few examples ago, actually. This is just the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n. And then we still have the dx part. Now that I don't think is too hard just to see right away because it's really 1 over 1 minus negative x squared. So it's negative x squared to the n, which amounts to this if you simplify a bit. But now to anti-derive each term, remember we can ignore the negative 1 to the n because it's a constant with respect to x. So really what we get is this, the sum from n equals 0 to infinity of negative 1 to the n, integral of x to the 2n dx, and the antiderivative of x to the 2n is, wait for it, okay, add 1 to the power, divide by that new power. So x to the 2n plus 1 over 2n plus 1. Good. So now I don't think we actually need to do any reindexing in this case like we did for ln. I mean, you can write it out to see what it is, but this is actually pretty nice as it turns out. And the interval of convergence here, by the way, is also, well, the radius convergence at least is 1. We know that part at least. And again, how I know that is because we actually argue that here, 1 over 1 plus x squared is only valid when x was, absolute value was less than 1. And we saw that in the previous example that we took a look at this particular function. So that I don't think is too bad. But remember, since we're anti-deriving, the endpoints can possibly be included in the interval of convergence. So for the interval of convergence, we actually have to check by plugging in these values. Now, if you plug in -1, it's kind of funny because this is an odd power. The power is 2n plus 1. And if you plug in powers of, well, if you plug in n equals 0 to infinity into this, I'll write this out actually. Here's what we get. So without the alternating part, just focusing on this, plugging in n equals 0 and then 1 and 2 and 3 and so on, we get x to the 0 plus 1, so that's x, over 0 plus 1. So really it's x to the 1 over 1. When you plug in 1, you'll notice the power is 2 times 1 plus 1, which is 3. So we get x to the 3 over 3. Similarly, when you plug in n equals 2, you get 2 times 2 plus 1 for these, which are 5. So it's pretty obvious what the next one will be. It'll be 7 because these are just the odd positive integers. And now for the signs, when you plug in 0, -1 to the 0 is positive, -1 to the 1 is negative, -1 to the 2 is positive, and so on. So this is actually the series we have here, but just expanded out term by term. Now, when you plug in -1, it's really interesting because notice this has no effect because the power is always odd. -1 to any odd power is always -1. Similarly, 1 to any power is also 1. So in reality, when you plug in -1 and 1, it doesn't actually affect the convergence or divergence. Really, we're just kind of ignoring this part. So when you plug in -1, it's kind of the same as plugging in 1 as far as convergence goes. So you can check that by trying it on your own. But basically what we end up getting is -1 to the n over 2n plus 1. In the case of -1, we get negative that sum. In the case of +1, we get positive that sum. And notice by alternating series tests, these both actually converge because it's a decreasing sequence that approaches 0 in the limit. And all those terms are positive if you ignore the alternating part. Great. So now, is there a nice consequence when we plug in either -1 or +1? There absolutely is. So I'm going to plug in +1 now. So in fact, here, just to show you, let me write for the consequence here. Let me kind of clean this up a bit. So I'm going to say when x is equal to +1, so this, again, by the way, this is our answer as far as the power series representation of tangent inverse goes. But when we plug in x equals +1, we get this, but with 1s instead of, so that's just 1. And this is -1 over 3, plus 1 over 5, -1 over 7, plus. So it's just the alternating series of 1 over the odd numbers. And that's equal, according to this, tangent inverse of 1. But what is tangent inverse of 1? It's pi over 4, because tangent of pi over 4 is 1. So in fact, we get actually a nice way you can approximate pi over 4 from this. The only issue, and you can actually check by an estimation theorem we saw on alternating series. I actually didn't focus on it too much, but it's in the book under the section of alternating series. That if you want to approximate this to a good accuracy, like even like 2 decimal places, you have to go out like I think 100 terms as it turns out. So it's not the most effective way of approximating pi, let alone pi over 4, but it is something nice that we kind of get as a consequence of power series in calculus. So I want to look at one more example. I'm not going to do anything crazy like I did with these two, but I just want to do one more example so we can try to see the techniques again that we showcased here to find the power series representation of a function. So let's take a look at that one more example right now. Right, so here for this last example, all I'm really going to do is find the power series representation of this function and write the interval of convergence and possibly radius of convergence. Now, this looks actually really similar to what we saw with ln of 1 plus x. In fact, there's a way to leverage that, I think. Let's see if we can write this as ln of 1 plus something. ln of 1 plus what? Well, notice this is 1 plus 4 minus x. So that would be our x here, and we actually know that the power series representation of ln of 1 plus x is the sum from n equals 1 to infinity of -1 to the n plus 1 of x to the n, but here this is our x, if you think about it like that. So it's going to be 4 minus x to the n over, see if we can do that, over, well, I guess it was just over n, wasn't it? Good. And this was valid when, well, let me see if we can write the radius of convergence. It was when x is less than 1, but notice this is absolute value of 4x now less than 1. Specifically, the endpoints, I guess we can just check by writing the interval of convergence. So here, what's the interval of convergence? The only problem is that this is not what we're used to. Here, the center really is 4. So if you want to, we can write this as x minus 4 because their absolute values are the same. I mean, if you think about it, really, this is just negative that. But in the absolute value, if they're negative, they have the same absolute value. So now the interval of convergence is centered around 4 with radius 1. So if you start at 4 and add 1, you get the larger limit, which is 5. And if you start at 4 and subtract 1 to get the first limit, you get 3. So this is 3 to 5 with probably closed here and open here, kind of like we saw for 1 plus x. Actually, it was the other way around for ln 1 plus x. It was open here and closed on the second one. So we'll see that. But before I get to that, I want to show something. So we have this series from n equals 1 to infinity of, I'm going to actually change this so it looks like the way we like, x minus 4. So really this is x minus 4. Let me see if there's a different way of doing that. That's fine. Negative 1 to the n times x minus 4 to the n all over n. Just like that. So I think this is actually not too bad. Now, of course, negative 1 to the n plus 1, negative 1 to the n. We saw this before when we multiply these. Basically, you just get, long story short, negative 1. So really, we can pull the negative out of the series and just end up getting this, which is nice. So it's non-alternating. And when we plug in 3, we get an alternating harmonic series which converges. So it is actually the opposite of what I said. And then here it diverges because 5 minus 4 in the base will give you just the regular harmonic series, which diverges. So I may have said that funny, but here it converges, here it diverges. The only issue is that this is centered around 4, and I wasn't intending on that. So I was just leveraging this fact that we already saw, and we got a center of 4, funny enough. Now, can we do it another way and not get a center? So let's say a center of x equals 0, so the normal just x to the n instead of x minus 4 to the n. I think we can. We'd have to do the same tricks we did for ln of 1 plus x. So I need to take the derivative and antiderivative. I think it'll be quick, so let me erase this and we'll try that real quick. Right, so this is one of our results, but now I'm going to say again that this is equal to the integral of the derivative. Derivative of 1 over x minus 5 minus x is, well, the derivative of ln of that is derivative of the inside, which is negative 1, over the original inside. Now we can legitimately do a different swap here and just call this 1 over x minus 5, but we want, for the power series, remember we want it to be 1 minus that. So what I'm going to do instead is I'm going to pull out the negative 1 and I'm going to pull out the 5. So I'm going to pull a negative 1 over 5, integral of 1 over 1 minus x over 5. And you can verify that on your own, but this is legit correct. And what we end up getting here is negative 1 over 5 integral sum from n equals 0 to infinity of x over 5 to the n, which is x to the n over 5 to the n, dx. Now the antiderivative of x to the n over 5 to the n is just the antiderivative of really x to the n and then that over 5 to the n. Because since 5 to the n is a constant with respect to x, it doesn't really affect the antiderivative. So this is negative 1 over 5 sum from n equals 0 to infinity of 1 over 5 to the n times antiderivative of x to the n is x to the n plus 1 over n plus 1, and then no dx now. But what we still do have though is plus c now, because when you antiderive you get plus c. Technically I guess it should be negative 1/5 plus c, but that's still a constant, so we can just leave it like that. And since these are all equal, we can just let x equal 0 to make this whole sum 0. And you can kind of see that even when n is equal to 0, we still get x here. So we legitimately get a sum of zeros. When you plug in 0 here, we get ln of 5. So this c isn't 0. This c is actually ln of 5. So that takes a little bit of justification in writing out, but I'll leave the details for you there just because I want to make this a little quick. And now we can re-index this by adding 1 here and subtracting 1 everywhere else. So what we'll get is, let me see if I can write this as ln of 5 minus this sum, which will start at 1 now instead of 0. Now, if you bring the 1 over 5 in, it adds 1 to this power, so let me show that in red. Bringing it in adds 1 here. And then increasing this to 1 will decrease all of those n's by 1, making the n plus 1s just n's. So really this is just going to amount to, let me write it like this, I guess, x to the n over 5 to the n times n. Or let me write it as n times 5 to the n. That looks a little better. There we go. And what is the interval of convergence here? Well, the radius of convergence, I guess here at this point was well, I guess 5, because you want the absolute value of what's taken to the nth power, which is x over 5 in this case, to be less than 1. Meaning if you multiply both sides by 5, you end up getting this. The absolute value of x must be less than 5, so that's our radius. So we know here the radius convergence is indeed 5, but the interval of convergence we still have to figure out by testing the endpoints. But here, since the center is 0, legitimately this is negative 5 to 5. And notice when you plug in negative 5, let's see, what do you get? Well, plug in negative 5 here, you get negative 5 to the n over 5 to the n. The 5 to the n's cancel. But since it's negative 5 to the n, you first have to split it up as negative 1 to the n times 5 to the n. So it'll actually be alternating. This part's fine. This is just finite terms. So that converges. But here this will be alternating. An alternating harmonic series converges. So it's closed there. When you plug in 5 here, the 5 to the n's legitimately cancel. So you're just left with 1 over n, which is a harmonic, which diverges. Cool. So we get something entirely different. So we got a pretty easy one relating to what we already knew, but it's a center of 4, unfortunately. Whereas here we get something entirely different. And in fact, if you let x equal 1, I said I wouldn't do anything crazy, but you can do that on your own if you want. So I'll just allow you to do that. If you want to find, let's say when x is equal to 1, if you want to find this sum from n equals 1 to infinity of, replace all x's with 1, so it's 1 over n 5 to the n. And notice we can do that because x equals 1 is indeed in this interval of convergence, then you can actually get a closed form for this. And it's actually not too bad. Let's see, when x is equal to 1, it's ln of 4, but remember we have this ln of 5 and it's negative, so I'll let you verify what it actually is. And you can plug in different values of x to get nice power series, well, let me say closed forms for different types of power series that have this form when x is certain values. So it's kind of interesting to see. And notice this is not just a geometric series because of this n in the denominator. I mean, you would say, okay, yeah, it's a geometric series of ratio x over 5, or in this case 1 over 5, but the n in the denominator changes things up a little bit. Anyways, I know I rambled on a little bit, and that actually concludes the video here for 11.9, and we really only have one section left for 11.10. This class in particular does not cover 11.11, which will be an application, a really nice application actually, of 11.10. But anyways, we just need to see 11.10. So I'll see you in the next video for 11.10. Thanks for watching. I hope you enjoyed. See you in the next video.